Okay. I don't know what happens then if I record it. Okay. What was I going to say? Oh yeah, homework. What do I have to say about homework? Oh yes, a few things about homework. I mean, most people did fine. Okay. There was a couple of things that popped up. First of all, there was the issue that I mentioned. Remember where I said, you know, you have dx by ds is equal to u, dy by ds is equal to something like u sine x minus u t, probably, right? So if you make the mistake of integrating this one first, not thinking that x is a function of s, because this one tells you that x is equal to us plus x0, and that's certain conditions. And then you have to substitute this in here, so this is a sine us, right? And then when you integrate this with respect to s, then it's different than if you think that this is not a function of s, right? So I did warn you about this mistake, but some people still made it. Okay, so there's warnings, or maybe those people that weren't in class didn't even warn you about the mistake or whatever. So anyway, so that's one thing which is a common error, and that people did. So bear this in mind. If you have to do problems like this again, you know, that if you see an X in here, this thing. Oh, okay, that reminds me of another thing. Here's another thing, right? I want to do an example of this. Yeah, I guess this one you can do this way. Yeah, okay. So if I have dx by ds is equal to u, dy by ds is equal to u sine x minus ut, right? Some of you did this, right? Dy by dx is equal to u sine x minus ut divided by u. And then went from there. And this of course gives you y as a function of x immediately, right? Without doing any of the parameterization. Okay, how many people did this? Okay, so you guys that did this, tell me when you're allowed to do this and when you're not allowed to do this. Can you do it all the time? If you have like 2 variables. What do you mean if I have 2 variables?
Like you have x and y.
Well, I have 2 variables, right? X and y.
No, it's no. It's
yeah, if these things are not explicitly a function of s, now there's no s in here, I can do this. If there is an s in here, I can't do this. Right? So be careful, right? Because if this, if this had a, if this wasn't a t, this was an s, and you went ahead and integrated it just with respect to x, you would get the wrong answer, right? So, but if these things, like in the case this case that I gave you to start with, is fine. This is correct. You can do it. This will give you the right answer. Okay, y in terms of x, whether that doing that, because there's no parametric variation in here, explicit parametric variation. So you can do that. So a bunch of people did this, and I wasn't clear that people knew why or how or when they can do it. A lot of times people will rely, right? So I wrote these things like this as dx by ds equals u, dy by ds is equal to v, right? A lot of times people will also write these equations as dx over u is equal to dy over v is equal to ds, right? Which looks like a rearrangement of these two things, right? And then you say, well, okay, let's just solve these two, which is what this is, right? dy by, so this one will tell me dy by dx is equal to, which way is it? dy by dx is equal to v over u, right? But this, you can only do this if these two are not functions of s explicitly, okay? So that is a short way of doing it if you know what you're doing, okay? But be careful with that. That's one thing. thing number 3 from the homework was that people were not very careful about initial conditions, right? So if I solve, let's say this one, dx by ds is equal to u, and I'm given that x equals 0 at, well, actually, let's do it at t, because this is the one that popped up, just so people are all clear. At t is equal to t0, or let's make it x equals x0 at t equals t0. Then, you know, this says that x is equal to, now, can I just write this? So I'm integrating this with t, and there's a constant x0 plus x0. Is that right? No, it's not right? There's some constant, let's call it c for constant, right? And then c has to satisfy this, but let's do this. X is equal to x0 when t is equal to t0, right? Plus c. So that tells me that c is equal to x0 minus u t0. So now I put it back in here. This tells me that x is equal to ut plus c, which is this, which is plus x0 minus u t0, right? So x is equal to, well, u t minus t0 plus x0. All the way I like to write x minus x0 is equal to u t minus t0, but that's just a rearrangement, it doesn't matter, right? But you can see this works, right? When t is equal to t0, that side's 0, and I get x equals x0, which is what we asked for. And this one does not do that. If I just wrote down this plus x0 when t is equal to t0, not equal to 0. If t was equal to 0, it's true, it would be x equals x0, but t is equal to t0, it's not the same thing. So you have to be careful. When I integrate things, I always write plus constant. And then I say, what does my constant need to be? Let's evaluate it in terms of x0s and t0s, etc. I tried to do that when I was doing it on the board, but then you do so many of them after a while, maybe I get too fast and maybe skip enough steps that it doesn't sink in enough, right? I'm sure you all understand this, right? You just have to do it. And a lot of people made a lot of mistakes with their, because sometimes I said, you know, it was x0, t0. Sometimes I said it was 0 at t0 and things like that. So, you know, when I'm asking for a streamline which goes through a point 0, 0, or a streamline which goes through a point x0, y0, these are different things, right? They give you different answers. So you have to be careful. Okay? I think that was it for homework. Yeah, anyone have any major questions about the homework? If you should always check what I put for your grade in Canvas. If it doesn't agree with what I wrote on your piece of paper, come and tell me, and we'll figure it out. I can't mark all questions, so I marked question 3, and then I looked at your pictures for question 4 to see if you got the idea of the sketches and what things were right. And I gave you a plus or minus or a squiggle, which means meh. Okay, about okay. So plus was good, minus was bad, squiggle is like okay. And I gave you an extra point. I didn't take away any points for minuses, but if you'd not done perfectly on question 3, then I gave you an extra point that looked like you'd done something interesting on question 2. Okay, that's the way it works. And then I gave you a percentage. Graduate students, I marked question 7 as well. Okay. All right, and of course I put solutions up, so you can go through my solutions. And my solutions does the first one this way. Just maybe a bit suspicious that you guys started doing this. You guys are not just searching the web for solutions and copying them, because that is not useful to your education. Right? Sure, that might get you a grade, but you won't learn it, but no good. Okay. Lecture over. No. Preaching over. Lecture begin. Yeah, lecture begin. All right, any questions about homework and stuff like that? How are we doing? Are you getting enough feedback on homeworks? I mean, do you need more? I mean, there's always my office hours. You can come and chat to me in office hours. Some people will be making use of that, but not many people. So, guessing everyone's doing okay. You're welcome to come chat to me. You can't make my office hour, my regular office hours, or you don't want to come and see the videos, just email me and make an appointment, okay? I am available to you guys. How are we doing in the course in general? I think it's bad to sort of ask you in person and make you say things. And maybe I'll have a little written thing. You can write something. How about that? But if, I mean, are we going too fast? Any general things that you're prepared to voice right now? You bored to tears? Are you excited? Is it fun? Is it?
I was just wondering that the textbook is pretty hard.
The textbook?
Yeah.
Ah, interesting. Okay. You should try reading Bachelor. It's much worse. You should read a bit of Bachelor, then try Kundu, and then you're like, oh, Kundu's great. Well, I mean, the things that I expected to know are all written in the lecture notes that I give you. In fact, the lecture notes have more than I expected to know. So everything that I do expect to know is in the lecture. Any other things while I'm just on a taking opinions thing?
The class kind of goes in pulses, like sometimes it'll go what feels like very quickly, other times it'll move very slowly.
Okay.
Like going through an equation very quickly sometimes, so you sort of hard to track what's happening on the board. Other times it's like a conceptual idea that's repeated over and over. I don't know if it's like a criticism, it's just a remark.
That's okay. I'll take on constructive criticism. Okay, so we need a signal for when things are going too fast then, right? You guys are allowed to stick your both hands up in the air and go, whoa, 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 whoa. Okay.
Sometimes when you write an equation, you'll work through a couple steps, and then you'll go back to that original equation and erase something and replace it with something else. Yeah.
Okay.
And that just makes it hard to take notes.
That's why I give you the notes.
Yeah.
Yeah, I understand that. That's in some sense, yeah. Every time I do that, I'm like, oh, this makes it hard for them. Sometimes I'm just trying to save time for myself a little bit. So yeah, I appreciate that, and I'll try not to do that. But everything is in the notes written out in steps in general, so you should have everything up. That's why I give you the notes, because I don't actually want you to, I'd rather you be concentrating and trying to figure out what I'm actually doing on the board than just trying to write it down. Because you have it elsewhere. If anything, print out the notes and come with the notes, and then you can add other notes to it or something like that. It's probably a better way to do it. Okay. Okay. We'll have sort of like a midtermy thing, which will have a thing on there where you can give feedback on the class and how it's going. So anyway. All right. So today I'll go really slow. All right, let me do this. Okay. Ooh, was it me that made this board such a mess on Tuesday? Oh. Well, today, I mean, it's a shame that it's a strike day and not everyone is here. It's an exciting day because by the end of today, you're pretty much done. By the end of the day, you'll know all the fluid dynamics. Because what we're going to do now, we did a bunch of stuff on inviscid fluid dynamics, right? Well, inviscid is a subset of all the fluid dynamics, right? We made an assumption that things are not viscous. Now we're going to do viscous fluids, and we're going to write out the equations for viscous flow. And, you know, if I write them out generally with sort of arbitrary forcing terms, you pretty much have all the fluid dynamics in those equations. So we're going to derive what are called the Navier-Stokes equations, which is it, all the fluid dynamics. Okay, let's get on with it. So, all right. Chalk. I had a decent piece of chalk. It's gone. All right, so okay, so we did inviscid, right? And we came up with these things called the Euler equations. And we talked a bunch about what we get out of the Euler equations. But now let's do viscous flows. Derive the equations, so figure out the equations for this. How do I want to start? Yeah, okay. So in terms of when we first started this class, the first thing we talked about was stresses as forces per unit area. These are surface forces, right? Body forces are kind of easier to deal with. The stress is a lot more complicated thing. And we said one of the big differences between inviscid and viscous was that they support stresses in different ways. You guys remember what it is? Inviscid fluids only support normal stresses, and viscous flows support normal and tangential stresses. So when we did this, I mean, forces per unit area normal to things, we figured out, all right, we can associate that with something, you know, a quantity which is pressure, right? So we have this idea of pressure. And pressure is really a hydrostatic, you know, thermodynamic sort of concept. But we use that in this sort of set. We said, okay, normal things, and we can say, and pressure is isotropic. It acts the same in all directions in this sort of business, right? So in some sense, we had, it was this, right? Here we had our stresses, but only the full stress tensor is tau ij, right? And we said, the only thing we have is this isotropic thing, and this is how we write isotropic things in terms of tensor notation. The only isotropic second order tensor is this delta thing, which means that it's just when I equals jx1, and when it's not, it's 0. So this just says this thing only has direction components which are minus b, minus b, minus b. Everything else is 0, right? This is what we have for inviscid fluid dynamics. These are the only stresses we have in inviscid fluid dynamics. Well, okay. Now for viscous flows, we want to work out. Now we have a tau ij. You know, it has everything. It has all 3 components. Sorry, all 9 components. 3 by 3 components. So the first thing you think is, and they're all different, right? There's no reason. I guess I could have written these down as tau 1 1, tau 1 2, tau 1 3. Tau 2 1, tau 2 2, tau 2 3, tau 3 1, tau 3 2, tau 3 3, and they can all be different, right? So the first thing you say is, well, I don't know. So what happened to pressure? I mean, we kind of like pressure, right? I mean, it's an intuitive concept, and we want to keep it around. So what am I going to do in this case? And so actually what people decided was like, well, okay, let's define something which looks like pressure and then just see what happens. Okay? So let's define pressure as, well, pressure was this thing, right, which was the diagonal terms. Here I have diagonal terms, right? Now they're all different. Here it was isotropic, so they were all the same. Now I have 3 different. So what's the nearest thing I can do? Well, it's always a minus, right? Well, let's take the average of these things, which will be tau I. So in index notations, if I have a repeating index, it sums, right? So this is this plus this plus this. And divide it by 3. That's the average of these things, right? So this thing gives me something which looks like a pressure, right? It's not exactly the same as this, unless they were all equal, but they're not equal. But you know, it gives me something which kind of looks like that, right? Okay. And then people said, okay, let's take my tau ij and say it has a bit like that, where p is defined this way, right? So it has a bit that looks like that, which is what I had before. But now, obviously, this is now, you know, this would kind of look like something like this, right? Which had equal bits. I don't have equal bits over here. So there's some bit, so there's some extra bits, right? Which we'll just call some other tensor, sigma ij. So this thing here, so this is an important thing. This thing here is the full stress tensor. This is our definition of pressure like this. And then this is the bit that deviates from that, right? It's what's that. So this is called the deviatoric. I love this name. Deviatoric stress tensor. It's the bit that deviates from our, you know, due to our definition of pressure. Now remember, if it's inviscid, this is exactly that. So there is no deviatoric stress tensor. But because it's viscous, we say, well, maybe it deviates from this. What will that deviation is like that? So this bit is due to non-isotropicness. All right. Okay. Right. So that's one thing. So we've invented some concept of rank here. Elliot's here. I have homework for you. Let me get out of the break. Okay. Right. So now our thing is, well, okay. We wanted to do something which we want to relate forces to what happens as a result of the force, right? And we said, well, there's a bunch of things we can do. We can create stress. Stresses can create strains and rotations, right? And all of this thing I said, there's some sort of stress-strain relation. And we had said, right early in the class, well, we thought there was some sort of relationship with this and velocity gradients, right? We said, a force creates a velocity, a shear force, for example, creates a shear velocity. And we said, well, okay, and there's some sort of coefficient between these two things. If we assume that these things are linearly related like this, there's some coefficient, and we called this thing the dynamic viscosity. And off we went like that to start with, right? Okay, but clearly this is too simple. It's too simple, right? Because actually, what I have is not just a tau, a single force. I have all these forces, right? I have 9 forces, 3 normal ones, and then all the tangential ones, 2 per surface, right? The tangential ones, another 6. Well, I have these. We said it's related to the velocity gradients. So these du's by dx's, let's call that. But this is du. This would be dui by dxj, right? There's 9 of these things too, right? Let's not use i's and j's because that's going to confuse us. Let's say k's and l's, right? Well, and I want to say they're linearly related. So any force can produce some sort of velocity gradient, right? The same as I just said, just for one force and one gradient. Now, there can be a, so I want to say this is equal to something, some constant, right? Let's call it A. But every single one of these components can be related linearly to every single one of those components, right? There's 9 of these and 9 of those. So every one of these has 9 of these associated with it, and every one of these has 9 of these associated with it. So how many constants do I need between 9 and 9?
81.
Yeah, 81, right? So I need this thing to have index I, J, K, and L, right? So this is a second order tensor. This is a second order tensor. So the constants between these things is like 4, right? So there's 81. So I have 9 things related to 9 other things, and every one can relate to everyone. There's 81 components of this thing, right? So when I say viscosity, there's 81 viscosities. Okay, there's 81 different viscosities. Okay, that doesn't sound so good, right? So we have to, we want to reduce this a little bit. We want to make this a little bit easier. We need to simplify this thing. Now, this is a little complicated, and I'm not going to go into tremendous details. I'm going to try and give you the idea of what's going on. Is anybody watching? No, nobody. Okay. All right. The first thing we're going to do is say, I remember we said, we did this little bit of work, right? It's like, well, okay, it's velocity gradients, but we can actually think of these in a slightly easier way, right? I can break this thing up into a symmetric part and an anti-symmetric part, right? And the symmetric part we called the deformation, right? So this was EIJ, and this is the deformation. And this was RIJ, and this was the rotation, right? And I don't know, do you remember how we defined this? We said Eij was equal to half dui by dxj plus duj by dxi. And Rij doesn't have the half, it's really annoying. Rij is equal to dui by dxj minus duj by dxi. So actually, this duk by dx, oh, I should have written k's and l's. This can be a k, and this can be an l. Doesn't matter, but this thing is equal to that plus a half that, right? It's kind of weird the way they define this because this looks like vorticity, right? Without the half. And then we'll say, okay, deformation looks like this. Okay, so one thing we can do here is actually say, well, these are stresses. We're interested in the stress-strain relationship. Deformation is the strain part. It turns out that all we're interested in is the relationship between these forces and the deformation they create. The rotation part is the anti-symmetric. This is why we break into a symmetric and anti-symmetric part. We're not actually interested in the anti-symmetric. It doesn't do anything for us. So actually what we're interested in is the relationship between tau ij, still has all these things, ij, kl, and ekl. This is a stress-strain relationship. So that's actually what we're going to try and figure out. Okay. Right. So this thing is a fourth order tensor connecting these two second order tensors. Now the thing we're going to say about stresses and strains is, once again, we're going to make an assumption that they're isotropic, which means that they don't care about, I mean, if they exist in this room and I looked in any direction, you know, the stress-strain relationship wouldn't change. Which is generally true for most things. There are some things like polymers, which isn't true, because polymers are very long chain molecules, and so they're different down the chain than across the chain. Right? But most fluids are not like that, not polymers and things like that. They're just regular molecules, which are pretty symmetric or isotropic with the same direction. So we should assume that this thing is, that these tensors are all isotropic. Right? So that's an assumption that we're going to make. And then one of the major simplifying things is that, and these are bits of math which I don't really expect you to be able to prove or anything like that, but it's helpful to have in your head. I can write all fourth order tensors, this I, J, K, L, in terms of, if it's isotropic, in terms of second order isotropic tensors. Okay?
I think I missed something. Why are we dropping the R term?
Because it's the anti-symmetric part. I mean, it's going to turn out that plays no, this stresses don't, and we're interested in stresses deforming things. The stresses aren't going to rotate things. Okay.
Is it because when you sum over an anti-symmetric tensor, it's 0?
Yeah, I mean, the product of an anti-symmetric tensor with any symmetric tensor comes to be 0. Yeah, that's right. So we don't actually care about that part. I mean, if you continue the calculations, this part will actually have no contribution. Okay. Fourth order, or actually any higher power order, or any even higher power order tensors which are isotropic, can be written in terms of second order isotropic tensors. What? Okay, isotropic tensors. Zeroth order tensors are what? Scalars. Isotropic? How many isotropic zeroth order scalars are there? I'm trying to see if you understand what isotropic means.
All of them?
Yeah, all of them. I mean, the number 5 doesn't care which direction you're looking, right? It's still number 5, right? Okay, first order tensors. What's a more common name for first order tensors? Vectors. Okay, isotropic vectors. How many are there? 1. What's a good answer? 90% of the time. Yes, 0. Yeah, there's no isotropic tensors, right? I mean, maybe the degenerate case of a 0 tensor is an isotropic one. It doesn't really care which way. So essentially, it's supposed to have directions. So that one's debatable. Okay, that's a degenerate case. Okay, second order tensors are matrices, right? There's only one second order isotropic tensor, and we talked about it when we did this, right? It's this one, delta ij. This is the only isotropic second order tensor. But what we're saying is that this thing can be written in terms of products. This is a fourth order tensor, so it can be written in products of second order isotropic tensors. It is isotropic. So you say, well, okay, I'm gonna get these in the order I wrote down. What are they? Well, delta ik, delta I there, JL. That's a product of second order isotropic tensors, right? But you know, because I have all these combinations of things, there are other ones, right? I can have, well, I can swap this around, delta IL, delta JK. These are different ones, right? Because they're different at different times. They have ones and zeros in different places at different times. And obviously I can have delta IJ, delta K. But these are the only products of second order tensors I can get. So what we're saying is this can be written in terms of, what am I going to use? Some coefficients times these things. Right? So this is just a well-known mathematical statement that these things are isotropic. I can do this. All right. Now we know some things. So this tensor is going to end up as a. I mean, this is a symmetric tensor. This is a symmetric tensor. This tensor is going to end up as a symmetric tensor. So tau ij is symmetric. In other words, sigma ij is symmetric, right? So that means this has to be symmetric in ij. It means that aij KL has to be the same as AJI KL, symmetric in I and J. Right? Well, if that's true, let's look at this thing. If I'm allowed to swap I and J around, then this becomes a JK and this becomes an IL, and this becomes a this is a JK and this is an IL. So it says that these two things, mu and mu dash, has to be equal to the same thing. So mu has to be equal to mu dash. Right, for that to be true. Okay. All right, that simplifies our life a bit. So that's telling me that sigma ij is equal to, now I have 2 mu, and I can pick which one of these things I call it, right? It doesn't really matter. Let's call it the first one. Delta ik, delta j, l. Plus I still have this, mu, double dash, delta ij, delta k l. Oh, sorry. If it's sigma ij, this was just my aij's, so it's this times my ekl, right? This is my sigma. So this actually, I can do something now. Let's do it. So what does a delta do? A delta says, well, it's only 1 when I is equal to k. So essentially what it does is swap indices here for the ones that I have here. So this one says swap a k for an I. This one says swap a j for an L, or an L for a j. So you can say that this is 2 mu. Now I want to use this delta, and it says swap a k for an I. So this becomes an EI. And this one says delta JL, so it says swap an L for a j. So this is EIJ. plus mu double dash. And this says, well, this is a delta KL, right? So it says swap a K for an L or swap an L for a K. So this one, if I leave, there's no I's and J's. There's nothing to swap here, right? So this one stays the same, delta IJ. And it says, well, swap a K or an L for a K or an L, doesn't matter. So I can call it EKK or I can call it ELL. Let's call it EKK, right? Is everyone okay with this? There's lots of indices, right? But okay. All right, back to tau ij is equal to minus p delta ij plus sigma ij. So the thing is we said we want pressure to contain the information about the diagonal terms, right? So actually what we want, so we want to say what's happening to the sigma ii. These are the diagonal terms, right? To the sum of these things, the sum of these terms. That's how we got our pressure, right? Remember pressure was equal to minus 1/3 tau ii, right? So there's a sigma ii bit here. What is it? Sigma ii is equal to, well, it's this, right? So it's 2 mu EII plus mu double dash. Now, this is, if I'm doing this II, this becomes delta II. And this K's are still KK's, right? Nothing has changed there. Okay. Well, what's the difference between EII and EKK? Nothing. They're the same thing, right? It doesn't matter. This is just a dummy index. All it says is that it says repeat. You know, I and I says repeat 1, 2, 3. E11, E22, E33. This says the same thing except the dummy index equals K. So these are actually the same thing. So this is 2 mu plus times E, whatever one you want to call it. Call it KK in my notes. Okay, what's delta II? 3, yeah, right? It's delta 1, 1 plus delta 2, 2 plus delta 3, 3. When I is equal to j, it's equal to 1. So it's 1 plus 1 plus 1. So this is 3, right?
Sorry, how do you go from delta ij to delta ii?
Here?
No, yeah, from there to, yeah.
Well, this is sigma ii, right? This is sigma ij. So it says set j equal to I, so that becomes delta I, right? Now the thing is, if I want my pressure like this to not have a plus sigma ii bit, you know, I want to keep my pressure like this. This is defined the way it was. I don't want a sigma ii, right? I don't want a sigma ii in here. So the way I have sigma ii not 3D double dash. So the way I eliminate sigma ii is to say, okay, let's set this equal to 0, right? 2 mu plus 3 mu double dash equal to 0. Now, this is an assumption. This is a way of saying I want to define my pressure this way. Right? This is us saying we are going to do this so that pressure is defined like this. So this is actually an assumption. This is a Stokes assumption. And obviously, this gives a relationship. So this says that mu double dash is equal to minus 2/3, right? Mu. So now altogether, I have sigma ij from over here is equal to 2 mu Pij minus 1/3 delta ij EKK. Right? What is good about this? Well, actually, let's keep going and just write down the thing that we were ultimately interested in. What we're ultimately interested in is tau, right? Tau ij is equal to minus p delta ij, and then plus this, plus 2u pij minus 1/3 delta ij dk. This is the relationship we were trying to derive. And this is called this is stress-strain, the stress-strain relationship. That's sometimes known as the constitutive relation. For these things, right? Okay, a number of things. This is one of those moments where you should be very, very excited, right? Which I know is hard to get out of you guys. It's hard to generate this enthusiasm. Why should you be excited? We started off with, I erased it, right? Tau ij is equal to ijk l, EKL. Right. How many were there?
81.
Yeah, how many are there now? Yeah. I reduced 81 coefficients to 1 coefficient, right? And this is the one we call, so mu is equal to the dynamic viscosity that we talked about before, right? So this is 81 coefficients reduced to 1 coefficient, right? And that's that one, the viscosity. So we reduced this whole complicated mess with a few assumptions down to this 1 coefficient. And we've incorporated some idea of pressure. And then I have 1 coefficient which relates this tensor to these tensors over here. And that's it. Right? Now, okay, what is EKK? Well, here's EIJ. Well, okay, maybe I'll make it easier. EII, which is the same as EKK, which is the same as Fred, right? It doesn't matter what you put in the bottom. What is EKK?
Divergence.
Yeah, absolutely. Can you guys see that? So let's make EII, right? Sorry, I'm doing it. I'm erasing things. Maybe I'm just going to apologize every time I do it. Oops, that is an I. That's an I, right? And now we have to do 1, 1 plus 2, 2 plus 3, 3, right? But look what this is. This is the half that plus half that. So that's just dui by dxi, right? Which is du1 dx1 plus du2 dx2 plus du3 dx3, which in my normal one is du by dx plus dv by dy plus dw by dz, right? Which is the divergence. Right? So this EKK is the divergence of u. Right? So this is cool because we're going to see some bits of this stuff drop out when we do incompressible things, right? So this looks like a nasty, nasty term, right? Nasty business. Okay. Now, this relationship is a linear relationship, right? It's a linear relationship between this tensor, and the coefficient of linearity is this thing. So these are linear relationships. And in real fluids, it doesn't actually have to be linear, but most fluids do have a linear relationship between these things. But the assumption of linear has a name, and this is called Newtonian. The Newtonian fluid. Once again, like I said, there can be non-Newtonian fluids. Like, yeah, you remember when I said, send me pictures of something cool fluid dynamics, and I said, but don't send me the pictures of the cornstarch stuff. Why? That cornstarch stuff is a non-Newtonian fluid. That has a stress-strain relationship where this coefficient depends on velocity. So this is a non-linear relationship. So that's cornstarch stuff is weird, right? It says it feels more viscous, more rigid if I try and move it faster. So if you stamp on it, it feels rigid. If you step on it slowly, it feels more fluid, right? That's the weird. Oh, did somebody join? David! David Allen Coulter. I'm celebrating. Hopefully I have him muted. Otherwise he's gonna be yelling at. I don't know whether he's or not. Anyway, okay. It's a bit late now. The hard stuff. Anyway, so this is the stress-strain relationship for a Newtonian fluid. Okay, which just means that this is a linear relationship. Is there anything else I need to say about that? Okay, no. All right, let's. Now David's here. Let's take 5 minutes break, David. Just take 5 minutes break, and and then we'll incorporate this into the equations. Now I want to say just one thing, okay? This is an undergraduate, graduate division. Now, graduates, you should understand this stuff. You should. I mean, this is all messing around with isotropic tensors. You need to. I mean, I don't expect you to be able to prove the mathematical theorem that this is always true or anything like that. But you should understand how we got from the beginning to here, right? Undergraduates, doesn't really matter. As long as if you understand what this relationship is and what it does when we stick in the equations, that's good enough. But on the other hand, it's useful for you to have seen it. I don't think it hurts you to have seen where it came from. Okay, now let's take 5 minutes break and we'll stick it in the equations. We're taking a break, David. Can you hear me?
Yes, I can hear you.
Oh, okay.
Yeah.
I can hear you too. So I need the information. I was going to try it. I don't think you can read the board hardly at all, but maybe you can hear some stuff. I don't know. I can follow along on the notes.
Well, yeah, so I can follow along the notes. And I wish I had checked my email just a little bit earlier, but yeah.
Yeah, I didn't send the email out until I just figured out whether it actually was worthwhile doing here. So I figured I might as well try it. Anyway.
Yeah, well, I appreciate it. Thank you.
All right. Oh, by the way, I think I'm recording this, so you can always play back the bits you missed.
Oh, perfect. Thank you.
How do I get myself out here again? Okay.
I don't know it's Steve.
Say it again.
Okay, yeah, stick it in there.
Let me see. Let me give you some. Here. Paul's still not here, right? Andrew's not here. Did you still need a stapler? Elliot's here. Who's this? Tonavi? Where's Tonavi? Did you still need a stapler? David, I got your homework. Adam, did you still need a stapler? Oh, there you go. Start back. Thank you. Good teamwork. John, are you dying over there? Don't die on us. Okay.
So, how do you promote the life relation?
How do I prove it's a new term?
Yeah.
It's an assumption. I mean, I guess you can test it.
Derivation is provided by the evolution of this derivation is provided linear way, then we can
Yeah, then the equations get more complicated, yeah, than just the pure differential equations. The things that I'm going to write up next depend on this being a linear relationship. I mean, there's ways that people do it. People will write this linear relation and then make viscosity a function of something. But if it's a function of velocity or anything to do with velocity, then it was incorrectly derived. But if you want to ask how do you actually test a real fluid, I'm not actually sure.
Yeah.
Presumably you can do some stress strain testing, right?
Since you want to use this equation, you must assume that.
No, but you can do it, right? I mean, you can calculate. I mean, you can calculate the torque on walls, for example, in a fluid. You can see if it's a linear relationship. So you can see if this velocity is the viscosity acts in a linear manner.
I was wondering, I guess you didn't take this out. I was wondering how this isn't constant because it's sine of 2 and 3 constants.
I mean, sure. The thing is, you didn't make any statement, right? You just wrote down an equation. You didn't show. I mean, the constant velocity is actually back over here, right? You have dy by dt is equal to a constant, and dx by dt is also equal to a constant. These are your velocities, right? This is just a trajectory.
Okay, yeah.
Not actually a velocity.
Right.
So,
Okay.
I mean, you didn't actually answer the question, but it's okay. But, it was there. You had it all there. So.
Yeah, I just thought that this was like something.
All right. Oh, I just bring my other. Where's that? Okay, let's get going again. All right. So now what we're going to do is just derive the fluid equations again, exactly the same ways we did before for the viscous stuff, but include for the inviscous stuff, but include the viscous parts, right? We always tell them to stop chatting and get in here. All right. So as before, I'm gonna sort of skip some steps as we go along now, right? But I'm just gonna do, we're essentially gonna do Newton's second law, force is equal to mass times acceleration again as we did before, in a Lagrangian volume. Here it is, and I'm gonna skip some of the bits, right? Because we talked about it in great gory details before. So this is the rate of change of mass per unit volume, right? Rate of change of momentum per unit volume. And this has to be equal to the forces, and we say, well, okay, there's a bunch of body forces, rho F, dV, those are easy to deal with. And then, the bit that's different between inviscid and viscous is perhaps the stresses. So these are surface forces. And, well, before we just had pressure here, right? We just wrote pressure straight in here. We wrote minus P N ds, but now we have a whole stress tensor. So I'm going to say, I'm going to write this in, I'm mixing vector and other notation here, but I don't know whether you prefer me to do this. I was going to write tau, oh, that's a horrible tau, ij, nj, ds. If you don't like mixed notation, this would be tau, but now I have to say somehow this is a tensor, and this is a dot product, a tensor dot product, right, with my n ds. So I don't know which of those you prefer. I mean, they mean the same thing, just in sort of different notations, right? But before we just had the pressure thrown into it, right? And now we're going to do all the same things as we usually do. This slide, everything's going to stay the same. Oh, but this one I can also write, now I want to write as a volume integral, right? Which means that I have to take the gradient of this thing, the divergence of this thing, right? If I want to go up to volume. So now I need to do divergences of tensors. So I can write that as, a divergence, noting that this is a divergence of a tensor, dot dv. Or another way of writing that is, and I think it's clear in this notation, right, is d by dx j of tau ij dv, right? It's not j. Right? So there's just a divergence theorem between here and here. But apart from that, all those things mean exactly the same thing. It's just different types of notation, right? And I think in some ways this index notation is a lot clearer for when you're dealing with tensors, because dot products are defined as, I mean, you have to define what a dot product means in the case of a tensor as opposed to a vector, right? So whereas here you're like, no, it just makes perfect sense. So it's a little bit easier. So anyway, this essentially, now I have, well, right over integral of v rho du by dt dv is equal to integral of v rho f dv plus that. So now everything's in terms of volumes. It's an arbitrary volume, so I can do my usual thing and just say this gives me the equation for the integral. Right? So now I'll write it in I won't mix notations. Let's just do it in indexes. Rho du by dt is equal to rho fi plus d tau ij by dxj. Right? This is a very, very general equation of motion, right? But not making any assumptions about the stress, that it's isotropic, it's just pressure and distance like that. So this is for a general stress tensor. And this one is actually called Cauchy's equation of motion. But okay, whatever. This is one of those things that's almost so general that it's useless, right? So now actually what we need to do is insert that stress-strain relationship to actually take it to something useful, right? So now we need to insert our tau ij equals Newtonian relationship, right? The constitutive relation. We need to insert that. So let's do it. So I have rho dui by dt is equal to rho fi. We're just keeping this general. Plus d by dxj. Now I just stick it in, right? And it was minus p delta ij plus 2 mu into eij minus 1/3 delta ij ekk. Close all my brackets. Okay. Left hand side is the same. Let's work on the right hand side. So minus rho fi, no change there. But look what I have. I have minus p dxj, but I have a delta ij. So this delta ij swaps j's for i's, right? So this becomes minus d by dxi of p. Now this is what we had before, right? So I had, when I did inviscid stuff, this was all that I had. I had rho dui by dt is equal to body forces and pressure. And this is the gradient of pressure, right? This is the same as grad P minus grad P. So we're back where we started before. But now I have to do stuff with these bits. Okay. So one thing I'm going to assume is I'm going to assume this mu, this dynamic viscosity, is actually a constant. This thing could depend on temperature, it could depend on, so it could depend on density, it could depend on certain things which depend on space. So maybe that's not always true. But a lot of the times that's reasonably true and we can assume that. So let's just start working through these terms. So now I have plus 2 mu times d by dxj, that's this d by dx of eij. So let's write eij out, that's a half dui by dxj plus duj by dxi. So I pulled out the 2 mu, I have the d by dxj, so this is the eij part, and I still have minus a third delta ij ekk, right? Which is divergence of u. Let's just leave it at that for right now. Right? Okay. All right, we need to figure out some of this mess a little bit, right? So let's write out the bits we still know. Rho dui by dt is equal to minus rho fi minus d by dxi of p, pressure, plus 2 mu. Okay, let's see what we got here. Well, okay, let's start multiplying it out. So this first term, I have a 2.5 here, so I can get rid of that. So I have mu times d by dxj of d by dxj of ui. That's this first term, right? Then I have another one, which is mu times d by dxj of duj by dxi. That's this term, right? And I still have minus a third delta ij ekk. I'm just leaving that alone for right now. Okay, that's good. Now let's see. Now, so this one is good. I'm actually going to leave this as this, right? This looks like a d by dxj, d by dxj. This is actually, you can write this as mu d2 by dxj squared of ui, right? This is a del squared if we went back to vector notation. Now this one I can write as plus mu. Now I'm allowed to swap around the order in which I do these things. This is a d by dxi of d by dxj mu j, right? Oops, and I actually missed something out over here. I missed a d by dxj out, right? Yeah, this one should have a, yeah, missed out all kinds of stuff. All right. Minus mu over 3 d by dxj of ekk, right?
Gradient of the divergence.
Yeah, this is the gradient of the divergence, right? Well, this remember, this one is div u, right? Well, so okay, so let's write it in here. We look at this one. Minus mu over 3 d by dxj of ekk.
It's 2
What?
2 mu.
Oh yeah, there's a 2. There's a 2. Yeah, there's a 2. Yes, thank you. Whoops. Yes. All right, thank you. All right, what is this? This is also the divergence, right? So this is the divergence of u. This is also the divergence of u, right? This is the same as EKK. I mean, it looks a little weird, right? Because EKK has a half something plus a something, but it's really just that, right? So this thing is also EKK or divergence of u, whatever you want to say, right? So this whole equation becomes rho du I by dt is equal to rho fi minus dp by dxi plus, now this one stays mu d2 ui by dx j squared. And now this one is, well, it's in terms of mu d by dxi, right? So I have mu d by dxi. And I have 1 div u, and I have minus 2/3 div u. So that just leaves me 1/3 div u, right? So you can say this is, should be plus or minus, no, plus, plus, 1/3 of, well, whatever you want to put in here, right? Div u or d, let's write it as that, du j by dx j. I mean, you can make these letters whatever you want, k's and k's, right? Doesn't matter because they're repeated. That's divergence of u. So here it is. Here's your equation. I mean, at this point, I actually think it is fairly useful to go back to vector notation because I don't know. I actually think a little bit more in terms of vector notation. But I mean, this is it, really. Let's write it. Let's put it up over here, and or maybe like it next to each other in vector notation. So let's write it next to each other. So rho du by dt is equal to rho times vector forces minus the gradient of p plus mu. Let's put this all in brackets. This is a del squared u, and this is a plus 1/3, and this is a d by dxi. That's also a gradient, and this thing, as we said, is the divergence of u, which is a scalar. Oops. So this is just another way of writing the same equation, but in vectors, right?
Remember the negative sign from the first term, rho of the force, yeah. Back to the other board, yep, at the very bottom, get it down, yeah.
Shouldn't have been there.
That should have been, okay.
I confuse myself because I always write left-hand side rho du by dt blah 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 equals minus gravity, but so I'm used to just writing a minus sign the first step after the equal sign, so that's a habit. Okay. Okay. This is the Navier-Stokes equation. Navier-Stokes equations, I guess there's 3 of them, right? These are the Navier-Stokes equations for viscous flow for information mode. Notice some things. I didn't say anything about rho, right? So these are compressible equations. And you know, now we've done all this manipulations to say, oh, these are viscous equations. So the Navier-Stokes equations are the compressible viscous fluid. I mean, we've not made any serious assumption. I mean, we've assumed that things are Newtonian fluids and things like that. We haven't made very many restrictive assumptions to get to this point. All right. So this is a very, very important equation. Okay. Having said that, does it sort of contain what we knew before? What about if we say, oh, it is incompressible? What about it is incompressible but viscous, still viscous, right? Well, what does that mean? That means that rho is equal to rho 0 and that the divergence of u is equal to 0, right? So then I would get rho 0 du by dt is equal to, now I'm going to write it, well, no, it's rho 0 f minus the gradient of pressure plus mu. But now that funny last term the gradient of the divergence disappears, right? This is it. And actually, you more often see this equation written like this, du by dt. Let's just take this rho 0, divide by rho 0. Oh, that's a vector. F minus 1 over rho 0 gradient pressure plus del squared u. And now I have mu divided by rho 0, which has this other symbol, which is mu. This is the Greek symbol that looks like this, right? So this mu is equal to mu over rho 0. And this is called the kinematic viscosity. And remember, as always, well, you know, this thing is equal to du by dt plus, well, I'm going to replace this right hand side. Du by dt plus u dot grad u, right? So this is a very common form of the equations, which is the incompressible Navier-Stokes equations. Okay. Maybe this is the easiest one. I mean, so this is it. You know, like I said at the beginning of this class, hey, guess what? You can go home now. There's fluid dynamics for you. All you have to do is you say, if you're interested in fluid dynamics, it's like, I don't know, pick your geometry and pick your situation, solve these equations, right? And you're done. That's everything, compressible, viscous, and everything. So we make it incompressible, makes that look like a little bit easier. And this is an equation we'll deal with quite a lot, just because incompressibility is a little bit easier stuff to deal with. But let's just play. Let's play the game of name those terms, right? And what is this term? Some of these are easier because we've been doing them for a while now. Yeah, this is Eulerian acceleration. What is this term? Advection. But what does it mean?
Waves.
It is the hyperbolic part of the equation, so it mean, yeah, you're moving wave packets around. That's one way of thinking about it. But it's the correction to make this a Lagrangian derivative, right? Which says if I'm Lagrangianly moving around in a spatial field, I might feel like I'm accelerating. My velocity might be changing because I'm moving, even in a steady field, moving from place to place. What's this one? What are these things? These generic Fs? Yeah, common one is G, right? Yeah, these are body forces. What is this thing?
Surface forces.
Well, all of these are surface forces, right?
Yep.
So this is the very particular, our new definition of what we're calling pressure forces. So this is pressure gradient forces. So a lot of times we'll just find it as the pressure gradient. It's the pressure gradient, it's the force which tends to cause an acceleration. And then this one, this term. What is this term? Does anyone know what this one's called? Well, it has a viscosity, so you can call it the viscous term, or you can call it diffusion, or viscous term. This is the term. This is the only term in this thing which depends on viscosity. I mean, we can go back over here and say in terms of kinematic viscosity. I'm not really worried about this one too much right now, right? Let's just say this term is easy to interpret. Well, what do we mean by viscosity? Does anyone have a feel for what this actually means? Let's give you some feel. Okay, I'll give you in words, and then I'll give you something a little bit more mathematical to back it up. Okay, this is the term which in fluids represents friction. Remember when we were first talking about stresses? I mean, I can only do shear stresses to deform things if there's some kind of stickiness between the layers, right? So if I put my hand on top of something and try and move it that way, unless just the top layer will slide unless there's some stickiness sort of making the other layer slide with it. So this is the equivalent of, this is fluid friction, if you want to think about it that way. Right? It's like a friction thing. It's like, I'm trying to move things by having a certain amount of stickiness to it. Okay? If you don't like to think about it that way, just think about this equation, but forget most of the terms, right? Let's think about, and let's make it one-dimensional, right? The u by dt, I mean, looks like or is equal to, let's say, just this term, mu, and we're making it one-dimensional, d2u by dx. Right? This is just this term and this term. So we're thinking about what is the effect of this term. So just take these two terms and think about what happens. Well, okay, if we wanted to solve this equation, we say, well, okay, I keep saying okay. What type of equation is this? It's a heat equation. In terms of classification of PDEs, you said right? It's not a wave equation. Yeah, it's a parabolic equation, right? This is parabolic equation. A wave equation is hyperbolic, and like this and this bit would be the hyperbolic part, the wave part. This and this bit is a different part. This is a sort of diffusive part. Okay? So if you don't understand that, it doesn't matter. Just remember what I'm going to tell you next is associated with parabolic equations, right? If I wanted to solve this, I might say, well, let's say U looks like, let's hope it's associated with some sort of some sort of coefficient which depends on time and some sort of bit which depends on space. So I actually want to say it has some bit which depends on time and some other bit which depends on space, like this. This is what's called a separable assumption. This is how you solve a lot of partial differential equations. I mean, this isn't always true, because I can have a function which is not separable. And in fact, if I do parabolic, I mean hyperbolic functions are not separable. But for these sort of equations, it works quite a lot. So in this case, let's just say A of t, and let's say we're trying to solve this problem in something which is sort of periodic. So let's just say this bit we can guess is looks like sine with some wave number kx, right? Because we're in a periodic domain, right? Okay, if we just bung this assumption in here, what do I get? I get A, which is the t, right? So dA by dt, no differential to this, sine kx is equal to mu. Now, differentiate this twice with respect to x. I still have my at, that doesn't matter. And sine goes to cosine, cosine goes back to minus sine, right? I get a minus, and I get a sine kx here, back to sine, but I get a k squared comes out of this thing, right? So just differentiate this twice with respect to x, I get a back to sine, but I get a minus k squared. Okay, this isn't 0 everywhere, so we can ignore this. So this just says that dA by dt is equal to minus mu k squared a, right? This is an ODE. We can solve this for a. What's the solution for this? This says that a is equal to e to the minus, well, some other constant, c, e to the minus mu k squared t, right? That says that this tells me that my velocity u looks like, so u, which is a function of x and t, looks like some constant e to the minus mu k squared t times sine kx, right? This is my solution to this little problem right here. So what does that say? That says, oh well, okay, if I start with something which looks like a sine like this, it has an amplitude of this sine. This is the amplitude of the sine, right? The amplitude of the sine, which goes like e to the minus something t, right? What's e to the minus? That's an exponential decay, right? So that says that as time goes on, this thing's going to go, right? So that's what this term tends to do. This term says, if there are any gradients, I'm going to sort of try and remove those gradients. I'm going to try and make them decay. Notice one thing here, it decays faster for higher K, right? Bigger K means that this decay is faster. So things which look like this will decay faster than things that look like that. Right? So, but that's what this term does. It says, if you have strong gradients, I will try and get rid of you. Okay. So that's what friction sort of does, right? If I have gradients, it tries to oppose those gradients. It tries to remove those gradients. Now, clearly, this thing, it can only do it up to the fact that that this thing becomes linear. If this u looks like a linear function with x, then this term goes away, right? So I can only decay gradients down to linear gradients. I can't decay them past linear gradients. So that's what the viscous term does. The viscous term is this thing which sort of says, okay, all this stuff is going on. Forces are stirring these things. I'm vecting things around. I'm accelerating things and blah blah blah. And what this term sort of says is like, whoa, 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 you guys are getting crazy and out of hand here a little bit. What are all these gradients you're creating? I gotta smooth things out of it. So another way you might want to think about this is, it's viscous smoothing, right? It's something which tries to smooth things. It removes gradients. Right? It's something very important I want to say next, but I maybe we didn't say it in the last 5 minutes. All right. I'll repeat this at the beginning of next class as well. Does everyone sort of get this idea of the feel of what's going on? We can go back to, actually, I'll just do this at the end of the class, and I'll do the next bit next time. We can go back to this equation, right? The compressible version. So if I play the compressible name the term game, what do I have of it? So this one is also rho curly du by d plus u dot grad u, right? So this has all the same bits as that one had. So this is this is Lagrangian acceleration, has an Eulerian acceleration and advection bit in it, right? Cool. Still body forces. Cool. Still pressure gradients. Cool. Still diffusion, right? This coefficient doesn't, in its mu form, does not have the dimensions of the diffusivity. This is the rho over here. The dimensions of diffusivity is this mu divided by rho. That gives you the dimensions of diffusivity. Doesn't matter. We still think of this as a diffusive term. It's still something which says, if there are gradients, try and smooth them out. Okay. Then there's this term. What do we call this term? Who has some ideas? What do you want to call it? It is the gradient of the divergence of u, right? So it goes away in incompressible. What else can we say about this term? Where does this term come from? It's definitely compressible, yeah, right? It says that if the divergence of my flow is changing in space, then I get an acceleration, right? It's like springs,
right? Because you gave me a look.
You are all exactly right. It's very, very hard to actually name this term what it is physically. It's a weird term. And in actual fact, the real reason for this term is the fact that we didn't really define the pressure correctly. This term entirely arises because of what we did to define our pressure, right? So this is, as you can see, it's about divergences, right? It's about things moving in the normal directions. And it's about, well, it says gradients of that. So maybe some bits are moving at different speeds than others, or different spatial, with space. They're changing differently with space than others. So actually, these terms, the bits are correcting for what we did here in terms of the pressure. Because the pressure, we said, we'll take the average stresses along the diagonals. And this is all about, well, if the diagonals aren't equal, then you get this thing, right? So yeah, I don't know. There isn't a good name for this term that I know of. Actually, if you can find one, I'll be interested. If you can find a good physical interpretation of this term as well, I'd be interested, because it's not completely obvious. But the way to think about it is, yeah, it's a compressible term that arises in the stresses due to the fact of the way you define the correction. It's a correction term. Okay. So yeah, when we play Name That Game, you know, you're perfectly at liberty to go this, and it's like, yeah. That's kind of what I do. And as you can see, in a lot of times, a lot of situations are really interesting, like incompressible stuff, it doesn't even make sense. And guess what? When we do vorticity equations, and we take curls of the equation, it's a curl of a grad, it goes away. So it's not the most important term around. But we don't want to call it that because we made it feel insecure. All this stuff. Okay, that's it for today. I know it's kind of an intense lecture, and it's a bit of a shame that it's during the strike action, so not everyone doesn't see it live and all sorts of business. But hopefully you got the idea. Ultimately, what you need to get out of this lecture is, oh, we derived the equations. It looks like what we had before, but we got some new terms, and really the most important thing about the new terms is they're related to this diffusive part, the viscous part, which is kind of like a friction, which sort of smooths fluids out. Okay. There's also a huge difference between these equations, all definable, but let's talk about the next class because I want to make sure everyone gets that. Okay. Any questions? I have no idea if we have a homework tonight. Sorry.
Can you put this online? This video?
I will do, yeah. If it did record it, I will put it online. Yes. All right. Questions? Any other questions? I have no idea if I'm sending you homework today or not. I'll have to go back to my office and figure it out. But look on the web and see if there is something.
It's kind of like directional spring resistance.
That's
A little lost here. We said,
Thanks, Nick.
this is equal to these two terms,
right.
and then we wanted to say that it's equal to this, or which is
Well, this is a, yeah, okay. It's equal to that, right? So then we turn it, so let's just say that it's, we're trying to relate sigma ij, which is the deviatoric part, to EAL.
So then did we, because I thought on the board somewhere we said that tau is equal to this.
Yeah.
But then, so then if it's equal to that and the other thing, then this is true?
Well, actually, no, we're trying to just do sigma ij is equal to that.
Oh, so.
You may have gotten those confused a little bit. Let's just check that here the way we're. So I'm trying to relate sigma ij to EKL.
Oh,
We're saying, okay, we've defined tau as this, so let's figure out this bit. We're trying to relate sigma ij to that, which is the deviatoric stress. We're saying we know what's bound to the branch, the deviatoric stress of velocity gradient, which then we run into just EKL.
okay.
That's what we're trying to do.
That makes sense.
I may have swapped a tau and a sigma at some point in there.
I think you might have just wrote it down wrong. But okay, that makes sense.
All right.
Thank you. Cool.
Let's stop this thing. Stop recording.